Looking at section 10.3, we have two new definitions. First one is scalar. That's just going to be a measure with a singular number quantity. So think of those as our constants. And vectors, these are measurements with magnitude and direction. There's a note that says magnitude is always positive. That's because for vectors, when we think of magnitude, we think of length. Since it does not make sense to have a negative length, we are going to make sure that our magnitude is always positive. For example, we have vector PQ. P here is our initial point, and that is what we are going to call our tail of our vector. Q is the terminal point, and that is what we are going to call the head of our vector. Notation-wise, notice that vector PQ looks a lot like ray PQ. There is a difference. Remember that rays do not have a length because they continue on forever. Since vectors have a length, they are going to be something completely different than what you learned about rays in geometry. Component form we have here, it looks like an ordered pair, except for parentheses, we do have these arrow brackets. When we talk about the magnitude of a vector, notice how the notation looks to be like taking the absolute value of the vector. Please make sure that you do not confuse magnitude with the absolute value. Now, how did we come up with this expression to find the magnitude? Well, in order to look at that, let's first circle back to our component form. So on the left here, we denote our component form, Vx and Vy, as the horizontal component and the vertical component of the vector respectively. Okay, so for our example of vector PQ, that horizontal component might look something like that, and that's going to have, let's say, a length of 4. Whereas if I look at the vertical distance between the tail and head, maybe that is a difference of 2. So when we denote the component form of vector PQ, we might call that 4, 2 with these arrow brackets. The reason why this is important, referring back to magnitude, is because now notice we have made a right triangle. Well, how have we found the hypotenuse of a right triangle in the past? Well, we have used the Pythagorean theorem. That's where this magnitude equation comes from. Also relating back to our trigonometry unit, we can find Vx and Vy by using cosine and sine of theta, where that theta is going to be the angle measure in reference to our x-axis. Remember, cosine is that horizontal component and sine is that vertical component in trig. So we just take those values, multiply by the magnitude of the vector, and we can also get these components for Vx and for Vy. Begin. Begin. In this unit, you will be asked to add two vectors together. Begin. In this unit, you will be asked to add two vectors together. Most important thing to remember is that when doing vector addition, we need to have head to tail. So what that means is the head of our first vector should be matching up to the tail of our second vector. Once we add these two vectors together, what will happen is we will get this third vector that we will end up calling u plus v. This will have a new direction and magnitude in comparison to the two original vectors. But what happens when you do not have head to tail? Well, if you have two vectors where their two tails match up, so in this example over here, vectors u and v match up at their tails, what we can do is we can complete a parallelogram, and the diagonal from the two tails to the opposite corner is going to be our u plus v vector. And the reason why this works is because, remember, parallelograms, opposite sides are congruent. So we can move vector v up here, or we can move vector u over here. In any case, this diagonal that occurs ends up being our u plus v vector. In this unit, you will be asked to add two vectors together. Most important thing to remember is that when doing vector addition, we need to have head to tail. So what that means is the head of our first vector should be matching up to the tail of our second vector. Once we add these two vectors together, what will happen is we will get this third vector that we will end up calling u plus v. This will have a new direction and magnitude in comparison to the two original vectors. But what happens when you do not have head to tail? Well, if you have two vectors where their two tails match up, so in this example over here, vectors u and v match up at their tails, what we can do is we can complete a parallelogram, and the diagonal from the two tails to the opposite corner is going to be our u plus v vector. And the reason why this works is because, remember, parallelograms, opposite sides are congruent. So we can move vector v up here, or we can move vector u over here. In any case, this diagonal that occurs ends up being our u plus v vector. Other vocabulary that we're going to run into for this unit is navigational vocabulary. So when we talk about the heading, we are talking about the direction if there is no impact from wind speed or anything else that can affect the direction of something traveling. We also have airspeed, so that is speed relative to the air, and ground speed, speed relative to the ground. In some cases, those two things are the same if there is no air effect. V plus W, that's simply going to be the course of something traveling in most cases. And our drift angle is just going to be that angle between the heading and course. So if I look back at this parallelogram law again really quick, that V plus W, that's going to be that U plus V that we found here. And then that drift angle is usually going to be the theta in this diagram. So for our example problems, for 1 through 3, we're going to use these points to graph the given vectors and then find the magnitudes. Looking at problem 1, we have vector QS. So I'm going to start by first just graphing the points Q and S. Point Q is going to be this point 4, 6. And S is going to be the point 5, 9. So we have that vector there. In order to find the magnitude, remember I need to find the horizontal and vertical components separately. So for the horizontal component, going from tail to head, that is a change of 1. And then vertically, we're going to have a change of 3. So when we go ahead and find the magnitude, we're simply going to have the square root of 1 squared plus 3 squared, and we get the square root of 10. For a problem like number 2, we're going to set it up the same way. Graph the 2 points first. So point P is -1, 3. And point O is my origin. So we have this vector here. For this one, our horizontal component is going to be 1, whereas our vertical component is going to be -3. So when I find the magnitude, we are going to have the square root of 1 squared plus that -3 squared, but it's going to be exactly the same as we got for problem 1, the square root of 10. Please note that even though these two vectors have the same magnitude, they are not congruent. In order for two vectors to be congruent, they must have both the same magnitude and the same direction. Since vector QS points more north and vector PO points more south, we cannot say that these guys are congruent. Okay, so then our last problem here, number 3, we are going to graph these two vectors, add them together, and then find that magnitude. So vector QP, again, Q is at the point 4, 6. So that's over here. And P is -1, 3. And so our first vector is there. And then our point R is at 4, 3. And so our second vector is here. For this problem, remember that we have two tails that are matching up. So in order to add these two vectors together, what we need to do is to finish the parallelogram that they create. So I'm going to notice that the point R is 3 spaces below point Q. So from point P, I'm going to go 3 spaces lower. And I know that this should be the parallelogram that I'm looking at. And so this new point, let's just call it X. From Q to X, that's going to be the addition of these two vectors. Okay, so if we need to find the magnitude of it, again, let's look for the horizontal and the vertical distances. So horizontally, from Q to X, we went -5. And from Q to X, we also went down 6. So when we go ahead and find that magnitude, we can say that this is the square root of -5 squared plus -6 squared. So we'll get the square root of 25 plus 36, which should be the square root of 61. For a problem like number 4, it's telling us to find the magnitude of F plus G and to find theta, which is going to be the angle between G and F plus G. This problem tells us that the magnitude of F is 4.06 newtons. So I know that this side over here, we can label it as such. And I also know that since we finish off this rectangle, this side should also be 4.6. It also tells me that the magnitude of G is 26.83, so we can label that. Since this is a rectangle denoted by that right angle, we can simply do the Pythagorean theorem. So the magnitude of F plus G is going to be the square root of 26.83 squared plus 4.06 squared. And when I plug that into my calculator, that should give me approximately 27.14. And we're going to keep the units the same, newtons. Now when I'm looking for theta, well, looking at this, again, we have a right triangle, so let's go ahead and use trigonometry. I can set up that the tan of theta should be equal to 4.06 over 26.83. And so when I take the arctangent of that fraction, we should get that theta is approximately 8.6 degrees. For a problem like number 5, it is telling me that the magnitude of F is 8 newtons and the magnitude of G is 10 newtons. So I'm going to go ahead and reflect that 10 over on the right. It is also telling me alpha. Now be careful. Alpha is this big angle between G and F. That is 60 degrees. So again, like number 4, we are going to find the magnitude of F plus G, plus we are going to find theta, which is just the angle between F and F plus G. Okay, so for this one, think back to your properties of parallelograms. If this bottom left-hand angle is 60 degrees, my bottom right-hand angle should be supplementary to it. So this angle should be 120. Now, if it's easier for you to see if I highlight, we are now going to be using law of cosines for this triangle to find the magnitude of F plus G, because we have a side angle side triangle. So that magnitude of F plus G is going to be equal to 8 squared plus 10 squared minus 2 times 8 times 10 times the cosine of 120 degrees. And if I plug that entire thing into my calculator, oops, I forgot F plus G, magnitude of F plus G squared. So if I plug this into my calculator, that magnitude squared equals 244. And so my magnitude is simply approximately 15.62 newtons. So now to find theta, again, I'm going to go back and use law of cosines to find that missing angle. So I'm going to set up that 10 squared equals 8 squared plus 15.62 squared minus 2 times 8 times 15.62 times the cosine of theta. So I should get that the cosine of theta is equal to 207.9844 over 249.92. And so then from there, we take the inverse cosine and get that theta is approximately 33.67 degrees. For problem 6 and 7, we are going to be finding the vertical and horizontal components of the vectors. So for 6, it tells me that the magnitude is 12 centimeters per second and theta is 120 degrees. Remember that my vertical components, so that was Vx and Vy, we found those by taking the magnitude, so 12, and for my horizontal components, the Vx, we are going to multiply by cosine of 120 degrees. And for Vy, we are going to multiply by sine of 120 degrees. When I plug those into my calculator, Vx should be negative 6 centimeters per second. And Vy should be about 10.39 centimeters per second. For problem 7, very similarly, Vx is just going to be, if my magnitude is 6.34, we will multiply it by the cosine of 175 degrees, and that should be approximately negative 6.32, and that will be newtons. And our Vy is going to be 6.34 times the sine of 175 degrees. And that is going to be approximately 0.55 newtons. For a problem like number 8, this is where we're going to be using vectors in navigation. So let's go ahead and pretend like we're flying an airplane. It's giving us some information about our airspeed, the wind speed, and then it's asking us to compute the ground speed. Whenever you do problems like this, I want you to make a note up top. For problems like this, we are going to use that resultant force. Or that parallelogram law, because that air, the wind speed, has an effect on my airspeed. So there's going to be some kind of resultant force that we're looking for, and that's going to be the ground speed. Another note that I want you guys to make is that angles are measured from north. And you'll see what I mean by that in just a second. Okay, so we're talking about moving here. First thing that I'm actually going to go ahead and do is do a quick XY plane, and we'll call it north, east, south, and west. Okay, so this part here tells me a heading is 30 degrees and airspeed is 300 miles per hour. So what that means is 30 degrees from north we are going to have a vector that is 300 miles per hour in magnitude. Okay, similarly, we are going to have wind speed that is 25 miles per hour from 120 degrees north. So 120 degrees should be somewhere here in my fourth quadrant. And what's special about wind speed is that we're always going to be traveling north. And so this vector is actually going to be pointing north instead of away from the origin. Okay, so remember how I said that for these problems, we are going to be using the resultant force or that parallelogram law. In order to use the parallelogram law, we need to make sure that these two vectors are both touching at their tails. Well, since they are not doing that at this moment, what we can do is we can take that wind speed vector and I can actually move it such that the tail end starts at the origin. And I could do this without changing the problem. Okay, once I do that, I'm going to recognize that since this was 120 degrees from north, if east is 90 degrees from north, this extra part from east to that original wind speed would have been 30 degrees. Okay, well, if that angle is 30 degrees, this angle here should be 60 degrees. Okay, and really quickly, that's because vertical angles, this one should have also been 30 degrees. And so the remaining part should have been 60. So now that I know all of that, again, we're using that resultant force or the parallelogram law. Let's go ahead and make a parallelogram. So I'm going to extend my parallelogram out that way and extend it out this way. And so the vector that I'm going to be looking for that is going to compute my ground speed is going to be this one here. And so in green is going to be my ground speed. Okay, well, the ground speed, just like the other two speeds, are just magnitudes. So let's find the magnitude of my green vector. How are we going to do that? Well, if you guys recognize, since in blue we have 30 and in purple we have 60, we have now made a rectangle. Because that's a rectangle, this makes our job really easy. That ground speed is going to end up being 300 squared plus 25 squared, and take the square root of that. And so that ends up being approximately 301.04 miles per hour. And that's the magnitude of that green vector. Okay, now for our drift angle. Our drift angle is going to end up being the angle from which I was originally traveling, so that blue vector, the angle between that and the green vector where I'm actually traveling. So this angle here is going to be my drift angle, and let's go ahead and call that theta. Okay, well, how do I find theta? Remember that up here, this vector should also be 25 miles per hour. So we can set up that my drift angle is going to be the tangent of theta is equal to 25 over 300. And when I take the arc tangent of that, we end up getting that it is 4.76 degrees. Our course angle is actually going to be the angle between north and my ground speed vector. So let's go ahead and call this angle alpha. If you recognize, remember that my original blue vector for my heading was 30 degrees. Notice that alpha and theta together should add up to 30 degrees. So we can say for our course angle that alpha plus theta should equal 30 degrees. And we already found theta to be 4.76 degrees. So our course angle should end up being 25.24 degrees.